So this video is going to cover the learning target I can check for an extraneous solution when solving a radical equation. Raising each side of an equation to the same exponent may introduce solutions that aren't solutions of the original problem. Since you're changing the problem, just because it works when the radical is gone doesn't mean it's going to be a solution when the radical is still there. So we do have to check those, and these are called extraneous solution. You should always check each possible solution in the original equation when you use this procedure. So let's look at this example down here. We have x plus 1 is equal to the square root of 7x plus 15. The first thing I need to do is, since my radical is already isolated on one side, I'm going to raise each side to a power that will eliminate that radical. In this case, I'm going to square each side. You will just be left with 7x plus 15 on this side. Please remember that x plus 1 squared means you have two of these. You will have to do the FOIL method. When you do the FOIL method on this side, you will end up with x squared plus 1x plus 1x plus 1 equal to 7x plus 15. Notice that you've got a squared term and x terms, which means that you're going to need to factor to solve this. So we will need to get one side equal to 0. I'm going to go ahead and subtract 7x. I'm going to write it here with my other x terms so I can combine like terms. I'm also going to subtract 15, and that will leave me with x squared. I've got 1x, and minus 7x, which is minus 5x. And then 1 minus 15 gives me minus 14. This is something I can factor and then solve for x. I am going to be looking for two factors that multiply to give me negative 14 that also add up to negative 5. And my two factors will be negative 7 and positive 2. When I set each of these equal to 0 to solve for x, I will have two possible solutions of x equals 7 and x equals negative 2. Excuse me. Now, what I need to check is do those solutions actually work back in my original problem? If you remember, the original problem was this. You're just going to plug each possible solution in one at a time and see if it actually works. If I plug in 7, I end up with 7 plus 1, or 8 on this side. When I plug it in over here, 7 times 7 is 49, and 49 plus 15 gives you 64. Well, the square root of 64 is 8. So I have 8 equal to 8. That is true, and so x equals 7 is a solution. Now, when I plug in negative 2, negative 2 plus 1 is negative 1. Over here, when I plug in negative 2, 7 times negative 2 is negative 14, and negative 14 plus 15 is 1. So I have the square root of 1. But that is not going to be equal to 1 because, again, thinking back to what we talked about in a previous section, since they basically started us with the positive root in this problem, we can assume that they want the positive answer. And so 1 does not equal negative 1. So we would not actually be able to use negative 2 as a solution for this problem, only the x equals 7. Another situation that may arise is a problem like this where you have a radical on both sides. You can automatically, it would be impossible to isolate both radicals on one side of the equation without introducing addition or subtraction. So as long as you isolate the two radicals on both sides, you can now just raise both sides or square both sides, and you will end up with 2x plus 5 equals x plus 7. Well, this is just going to be a linear equation. You would just need to solve for x. I'm going to subtract x from both sides, and then I will subtract 5 from both sides, and I get x equals 2. You should check to see if that is a solution in the original problem. And so if you think about the original problem, which was this, if you plug 2 in for x, 2 times 2 is 4, and 4 plus 5 gives you the square root of 9, which we know is 3. On this side, 2 plus 7 gives you the square root of 9, which we know is 3. So that does work in my original problem, so I can keep x equals 2 as a solution.